Critical web vulnerabilities are deterministic algorithmic failures. While often portrayed as digital magic, they're the inevitable result of system paths developers failed to model. Every application operates on a specific control flow. An exploit occurs when an attacker identifies a way to manipulate that flow, forcing the system to execute a path that was never intended. This map shows the intended lifecycle of user data flowing from client through load balancer and web server to the database. A malformed input forces this logic to diverge, splitting data into an adversarial control flow that bypasses security checkpoints. Now, we will reverse engineer three specific mechanics. First, injection attacks. Second, logic bypasses. And server-side request forgery. By tracing these to their exact lines of algorithmic failure, we can see how they function as structural flaws. Hacking is the mathematical weaponization of a system's own logic against itself. Web applications face a constant structural challenge. Data must travel across different execution contexts. A variable that begins as a text string in a web form may end its journey as a command inside a database query. Algorithms that rely on simple string concatenation fail to maintain a trust boundary during these handoffs. They treat the user's input as part of the system's own instructions. This abstract syntax tree shows a database parsing a query. Normally, user input is isolated within a data literal node, remaining passive. When an attacker provides syntax like OR 1 equals 1, the parser misinterprets the context. The malicious input sprouts unauthorized execution branches that climb into the tree's core logic. The engineering solution is the parameterized query, which changes the parsing sequence. The query tree's structure is fixed in place before user data is evaluated. When the malicious payload arrives, it is strictly constrained within the data literal node, unable to alter the tree's shape. Parameterized queries provide a mathematical guarantee that data cannot escape its context to become executable code. Beyond localized parsing, we must examine macro-level structural flaws, specifically how an algorithm moves through different operational phases. This checkout process is a state machine. To reach the confirmation node, the system must first pass through validation and payment. Each step requires specific preconditions to be met before the flow can advance. These preconditions are the invariants, the absolute truths the system relies on to remain secure. If an attacker modifies a hidden price field, they invalidate these preconditions, effectively removing the payment node from the active state logic. Trusting the current state, the algorithm reroutes the connection, bypassing validation and moving directly from cart to confirmation. Securing this requires moving all state tracking to the server side and enforcing it with cryptographic session validation. An algorithm's invariants must never rely on client-side assertions, because the client environment is under the attacker's complete control. The final exploit class, Server-Side Request Forgery, moves the failure from application logic into network topology. This is the confused deputy problem. Here, an attacker tricks a highly privileged internal algorithm into performing an action they cannot perform themselves. This occurs when web servers accept URLs from users to fetch external resources, such as profile images or remote webhooks. URL parsing algorithms often fail due to inconsistencies between the library that validates the URL and the one that fetches it. The server evaluates the attacker's input, pivots, and aims a request inward, behind the perimeter firewall. The internal API grants access because it assumes the request originated from a trusted internal node. It returns sensitive data to the web server, which then passes it back to the attacker. Defending against the confused deputy requires strict allow listing and the total disabling of untrusted protocol handlers. Internal networks cannot rely on implicit geographic trust. They must validate the original context of every request, making firewalls a secondary layer of defense rather than a primary one. When we revisit our initial architecture, the fragility of implicit trust becomes clear. By applying context boundaries to queries, rigid constraints to state machines, and zero trust verification to networks, we create a hardened architecture. Adversarial actions become unexecutable anomalies. Because deterministic constraints are absolute, red inputs bounce off without triggering a breach. A modern security engineer functions as an auditor of algorithmic determinism. To secure a system, you must stop treating user input as passive data. you must treat it as untrusted code actively seeking